Hello, week 10. We're starting chapter 13 on real numbers. So in this video, we will talk about the completeness axiom, the least upper bound property. And then we'll talk about metric, or how to measure distance in real numbers. And then eventually get to the definition of a limit. So that's the goal. Let's jump right to it. Okay. So real numbers. So the types of argument that we're gonna make in this chapters are going to be radically different from what we've done when we talked about integers and rational numbers. So I do realize that this is a little bit of a learning curve, but the payoff is so good that I hope you'll stick through it. All right, so let's review what the completeness axiom was. So in the first chapter, we discussed real numbers as complete ordered field. We went in depth about order axioms and the field axioms, but we kind of brushed off completeness axioms and say, oh, you need this for the limit. So let's get right down to it. Okay. All right, so let's say you have any non-empty set S of real numbers, and we say alpha, real number alpha, is an upper bound of S if every element in S is no bigger than alpha. So alpha is greater than or equal to any and all elements in S. Then we say alpha is an upper bound. Note that alpha does not have to be in the set S itself. It could be, but it doesn't have to be. So if alpha happens to be in S itself, then we usually call that alpha a maximum element of S. But alpha does not have to be in S. So that's how you define an upper bound. But that's not quite what we want. What we want to talk about is the least upper bound. So we say an upper bound is the least upper bound, or another word for it is the word supremum. Supremum of S, if S has no upper bound less than alpha. So alpha happens to be an upper bound and there's no smaller upper bound than that. Then we say it's the least upper bound. And we're going to use this frequently. So there's a notation made up for it. So if you write sup of S, you kind of read that as sup of S because it's sup is short for supremum. That's how we're going to write that. Okay. And we can clearly define a similar definition as well. So you could talk about lower bound, where beta is a lower bound if every element in S is greater than or equal to that lower bound beta. And if there are no larger lower bound, we call that an infimum. And then we'll denote it as inf of S. Okay, so here's the completeness axiom, or it's also called the least upper bound property. Every non-empty subset of R has an upper bound. Every non-empty subset of R that has an upper bound has a least upper bound in R. So you have to, before you can apply this axiom, you have to know two things, right? So if you have a subset of R, it has to be non-empty. So you have to show that there is at least one element in there. And not only that, that it has an upper bound. So it could be unbounded, right? Then it doesn't have a least upper bound. So if it's non-empty and it has an upper bound, then automatically you're given the what's called the least upper bound, or the supremum of that set. So this is true for real numbers. It turns out that it's not true for rational numbers. So here's a concrete example that shows that no such thing is there for rational numbers. So if you look at a set of rational numbers whose square is strictly less than 2. So it turns out that there is no least upper bound of this. You could clearly pick something that's larger than that. So for example, if you pick x of 2, anything that you squared and it's less than 2 is going to be less than 2 itself. But it's not the least upper bound, because the least upper bound would be square root of 2, but that's not a rational number. So if you pick any rational number that's above that, then by a rational density theorem, you can pick any number between the upper bound that you just named and the square root of 2 and get a closer upper bound, but it's still an upper bound. So rational numbers does not have this property. I hope that made sense. Okay, so let's talk about examples. All right, so let's look at the interval from 0 to 1. So this is my set S, any real number where it's strictly between 0 and 1. This is clearly bounded, so you can pick any number greater than 1 and it's an upper bound. The least upper bound would be exactly 1. So 1 is going to the supremum of the set from 0 to 1. If you pick any number below 1, then it's no longer an upper bound for the set between 0 and 1, because you can pick a number above that. If you looked at a closed interval, 0 less than or equal to x less than or equal to 1, again, 1 is the supremum of the interval from 0 to 1, including the endpoints. So in this case, 1 happens to be inside of the set. 1 is included, but it's still an upper bound. You just have to be greater than or equal to every element. It could be equal to. So even though the right endpoint in this set is included and this set is not, it doesn't matter. 1 is still the least upper bound for both of these intervals. If you're looking at the set of natural numbers, which is, you could think of it as a subset of the real numbers, this thing is not bounded, right? There is no upper bound of n. You could use Archimedean property for that. So it doesn't have to have a supremum. That's okay. In fact, actually, usually when you have a non-empty set that's not bounded, sometimes people will say, well, infinity is the supremum. But infinity is not a real number. So this does not count as the least upper bound existing. Let's see, let's look at the next one. So arctangent is a graph that looks like that. It gets closer and closer to pi over 2. And closer to negative pi over 2. So the image of the arctan function is the interval from negative pi over 2 to pi over 2. So the supremum for that set, supremum of image of the arctan in the domain, of real numbers is going to be pi over 2. It doesn't touch pi over 2, but it gets close to pi over 2. Let's see. Let's look at the next one. The set 1 over n. So we're looking at the set of 1. 1 over 1 is 1. 1 over 2 is 1/2. 1 over 3 is 1/3, 1/4, and so on. So the supremum for this set is going to be the largest element here at 1. So the supremum of this guy is 1. The next set, let's see, -1, -1/2, -1/3, and so on. So this set gets closer and closer to 0. The supremum of this set right here is 0. Right? There's a lot of negative numbers. 0 is greater than or equal to all of those. But you can't pick any number smaller as an upper bound, because as soon as you pick a number, then there's a negative number that's small enough that's above it. So 0 is the least upper bound here. Okay, I hope all of those examples made sense. Okay. All right, so we're at the end of the quarter, and we can't go too deeply into this, but I just want to mention that if you want to self-study this textbook, this chapter and the 4 chapters following it will actually walk you through calculus in a rigorous way. So what I mean by that is a lot of you have already taken many calculus courses, and taking calculus at freshman, sophomore level kind of allows you to know all the tools that you need about rate of change and accumulation of change in science and some computer science and applied fields. But if you want to go a little bit deeper into pure mathematics or theoretical computer science, maybe at a graduate level, then you actually have to know how everything is proved in the background. So the analogy that I make here is more like in calculus class, you learn how to drive the cars. But in real analysis, you'd have to become a mechanic, and you have to understand why these engines and things work and how they fit together to be able to diagnose a problem or suggest to build a tool for your particular purpose. So if you like to learn the calculus at a deeper level, those chapters is something you might want to look at. And after completing this course, you are eligible to sign up for a real analysis course, so senior level mathematics course that will go deep dive in those topics. All right, so before we get there, there's a basic tool that you need to use, and that's the notion of metric. Metric, from the name, maybe you've heard of metric system. A metric is a way to measure distance in mathematics. And here are the rules. So you have to have a metric paired with some kind of set. So in this case, our metric is going to be on a real number, but let me say the definition in a little bit more abstract way so it could apply to other things. So metric is a function on 2 elements in a set, so x and y. And it's called the metric on a set if the following 4 rules hold. Okay. If you plug in 2 different points in the set, you always get a positive number. So the notion of distance should always be positive. And if you plug in exactly the same element from the set, the distance should be 0. So if you plug in the same number, you get 0. The notion of metric or the distance should be symmetric. So the distance from point X to point Y is exactly equal to the distance of point Y to point X. That's a symmetric condition. And then one more. You need, for the distance to really make sense, it should be shortest distance between 2 points. So what triangle inequality has to hold. So if you're measuring a distance from X to Z, then that's smaller than starting with X, taking a visit to Y, and then going from Y to Z. So the reason why it's called triangle inequality is because you can kind of draw out 3 points X, Y, Z. The distance from X to Z should be shorter than first going to Y and then going to Z, right? Because you're taking a detour. So that's what this 4th condition enforces. And as long as these 4 things hold, we say it's a metric. And a lot of notions you build going towards calculus, like things like limits or derivatives. These things you could start to make sense of. But the way we can approach this is if you keep it a little bit more abstract, not use numbers, but use this idea of metric, then you could extend the notion of all these derivatives and integrals into different types of spaces. For example, you could talk about distance between different functions, or distance between different quantum spaces, or there are other ideas that you could attach to these things and do calculus out of. So that's why this is here. Okay. All right. So the metric that we're going to use for real numbers is the absolute value function. So metric between 2 different numbers is you take the difference and you look at the absolute value of it. Now, you look at this and kind of go back to the 4 conditions. Just making sure it kind of works, right? So if you look at a difference between 2 different numbers, you take the absolute value, that's going to be a positive number, unless X and Y are equal to each other, right? So if they are equal, then absolute value of the difference is going to be 0. It's certainly symmetric, right? Absolute value of X minus Y is exactly the same thing as absolute value of Y minus X. You could prove that by factoring out -1 from it. And looking at absolute value of -1 is 1, so it doesn't change the value. And the triangle inequality that we proved in chapter 1 was the triangle inequality for absolute values. So in that setting, this will translate to the difference between X and Z is less than or equal to absolute value of X minus Y plus absolute value of Y minus Z. So that satisfies all 4 of those conditions. Okay, all right. So now that we have a metric, we can talk about limits. So we can talk about our notion of limit. Okay, so let's talk about a sequence. So if we have a sequence of real numbers, we could talk about its limit L as a real number if the following condition holds. Okay, so this has a couple of quantifiers. So it's a little bit involved sentence, but let's parse through it. So for every epsilon greater than 0, there exists a natural number n such that if little n is greater than or equal to that n, then the distance to the limit is less than epsilon. Okay, so there's writing up the quantifiers. For all epsilon greater than 0, there exists natural number n such that once you pass that point, then the sequence is close to the limit. And the tolerance of how close you need to be is set by that epsilon. So epsilon could be as small as you like, but it has to be positive. Okay, and if you can show that this is a true statement, then we say the limit exists and it's equal to L. We also say the sequence converges whenever there exists a limit, and shorthand for writing all that. So it could be the name of the sequence, arrow to the limit real number L. Okay, or of course, you're probably more used to this notation that you're familiar with from calculus. Limit as n goes to infinity of n equals to L. So if you write this down, that's equivalent to shorthand for this mathematical statement being true. Okay, so let's apply it to an actual example. So let's look at a sequence of 3 plus 2 over n. Okay, so if we plug in different numbers for n, you might realize that, oh, this number gets closer and closer to 3 because it's basically 3 plus 2 divided by a number, and that number gets larger and larger. So that fraction part, 2 over n, is going to get smaller and smaller, and eventually it's kind of negligible and it's getting close to 3, right? So intuitively, maybe you can understand that, but let's use the definition, right? So for every epsilon greater than 0, there exists n such that n greater than n implies that inequality holds. So we have a candidate for our limit. So our L is going to be 3. Okay, so let's prove that the limit is in fact equal to 3. Right, so when we do these types of proof, if you want to show that the limit exists, you start with the sentence, let epsilon greater than 0. So let epsilon be some arbitrary number, and your next task is to use this epsilon to come up with an n, capital N, such that you can get close to the limit L as close as you like, or within epsilon. So what we're going to do is Archimedean property. So choose n such that n is a natural number greater than 2 over epsilon. And the reason why I did that is because this inequality is equivalent. If you shuffle around epsilon and n, you could show that epsilon is greater than 2 over n. And 2 over n is something that appears in the sequence. So you might, that's a hint at what's happening here. All right, so I want to show that this n is good enough to be epsilon close to the limit 3. So for all little n greater than or equal to n, we want to show that this absolute value, this distance from the sequence to 3 is small, or it's within epsilon. So the first step is for me to replace an with the definition of an, 3 plus 2 over n. And immediately 3 here and 3 there cancels out. So you only have 2 over n, and that's a positive number, so I'm just going to drop the absolute value sign. Remember that little n is greater than or equal to capital N. So if you replace little n with capital N, that's a smaller denominator, which means it's bigger, right? So 2 over capital N is bigger or equal to 2 over lowercase n. And going back to this inequality, we know that epsilon is greater than 2 over capital N. So 2 over n is less than epsilon itself. So in this chain of equality and inequality, we show that the distance from an to 3 is less than epsilon. Epsilon was an arbitrary number, so this shows that that this statement is true, right? As long as we're greater than big N, that implies that we're close, less than epsilon away from the limit. So the limit of an is in fact 3. I hope that made sense. This seems very involved. It does take getting used to, but hopefully at least this example makes sense. And then we'll look at how we can use this definition for limit to prove a couple of theorems on the next video. Okay. I will see you then.